You ever wondered why nothing can go faster than light? It's a question that has fascinated scientists, philosophers, and dreamers for centuries. The speed of light, a swift 186,282 miles per second, is often referred to as the universal speed limit. But why is this so? What makes light so special? The answer lies in Einstein's theory of relativity. Einstein proposed a revolutionary idea, that space and time are not separate but interconnected in a four-dimensional structure known as spacetime. And within this spacetime, nothing can exceed the speed of light. This isn't just a rule, it's a fundamental law of the universe, a cornerstone of our understanding of physics. But why can't we exceed this speed? Well, the closer we get to the speed of light, the more energy we need. And as we keep adding energy, we don't get faster, instead, our mass increases. Eventually, we'd need infinite energy to reach the speed of light, a requirement that's impossible to meet. In essence, the universe has set a speed limit that can't be broken. But what's even more intriguing is what happens to time as we approach the speed of light. This is where the concept of time dilation comes into play. Time dilation is a difference in the elapsed time as measured by two observers due to a relative velocity between them, or to a difference in gravitational potential between their locations. In simpler terms, the faster we move, the slower time moves for us relative to someone who is stationary. So, if you were to travel at near light speed, you'd experience time at a slower rate than someone standing still on Earth. It's a mind-bending concept, but one that's been proven true in numerous experiments. So, if nothing can exceed the speed of light, what happens when we try to imagine something that does? Well, that's where things get really interesting and we start to venture into the realm of time paradoxes. But that's a topic for our next scene. Until then, remember, in our universe, light doesn't just illuminate our world, it also shapes our understanding of time and space. Scene script. Let's dive into the realm of theoretical physics. Imagine a world beyond the speed of light, a world where time and space bend to the whims of particles zipping around faster than any we've known. These particles are known as tachyons. Tachyons are purely hypothetical, but they serve as a fascinating probe into the nature of our universe. Tachyons, if they exist, don't play by the rules set by light speed. Instead, they exist in a realm where they can flit from one point to another faster than light itself. Now this might sound like something out of a science fiction novel, but it's a concept that has been seriously considered in the field of theoretical physics. In this fascinating world of tachyons, some very strange things start to happen. One of the most puzzling is the violation of causality. In our everyday world, cause and effect have a clear order. You push a button, and a light turns on. But in the world of tachyons, this could all be reversed. The light could turn on before you ever push the button. This violation of causality is what leads us to the concept of time paradoxes. Time paradoxes are situations where an effect happens before its cause. It's like baking a cake before you even decide to start baking. It's mind-bending, to say the least. The existence of tachyons would mean that our understanding of time and causality would need to be rethought. It opens up possibilities for time travel and other paradoxes that challenge our fundamental understanding of how the universe works. But it's important to remember that all of this is purely theoretical. Tachyons have not been observed, and their existence remains a topic of debate among physicists. They serve as a tool for exploring the boundaries of our understanding and pushing the limits of our imagination. But how would these time paradoxes work? The answer to that question takes us even deeper into the fascinating world of theoretical physics, a world where time, space, and causality are just pieces on a cosmic chessboard, waiting for their next move. To understand time paradoxes, we need to delve into the world of time travel. You see, a time paradox is a theoretical conflict or contradiction that could occur if one were to alter past events. It's like a puzzle that defies logical resolution. The most famous of these is perhaps the grandfather paradox. So, let's imagine you found a way to travel back in time. You're excited, you're nervous, and you decide to meet your young grandparents before they've met each other. But then, in a series of unfortunate events, you inadvertently prevent them from ever meeting. Now here's where the paradox kicks in. If your grandparents never met, they never had your parent, and hence, you were never born. But if you were never born, then who traveled back in time to prevent your grandparents from meeting? This is the grandfather paradox, a mind-bending loop of causality and consequence. Now you might be wondering, what if I could go back and fix everything? Well, that's where the concept of a self-consistency principle comes in, suggesting that any actions taken by a time traveler would have already been part of history. So, in theory, you couldn't prevent your grandparents from meeting because, well, you exist. However, this doesn't fully resolve the paradox. After all, if you did manage to change the past, then you'd be creating a new timeline, a different reality where you don't exist. But then, where did the original you come from? This leads to the concept of multiple realities or multiverses, but that's a rabbit hole for another day. So you see, time paradoxes are not just a cool sci-fi concept. They challenge our understanding of time, causality, and reality itself, creating complex and mind-boggling situations. As we can see, time paradoxes can create complex and mind-boggling situations. Now, let's connect the dots between faster-than-light speed and time paradoxes. We've already established that going faster than light is a concept that challenges our current understanding of physics. But have you ever wondered what else could happen if we could exceed the speed of light? Well, one possibility is time travel into the past. You see, according to Einstein's theory of relativity, as an object approaches the speed of light, time around it begins to slow down. This is called time dilation. Now, theoretically, if an object could surpass the speed of light, time would not just slow down, it would actually reverse. This hypothetical scenario would allow for time travel into the past. But here's where things get tricky and paradoxical. Imagine you were able to travel back in time and somehow prevent your own birth. This is known as the grandfather paradox. If you were never born, then how could you have existed to travel back in time in the first place? Such paradoxes are mind-boggling and present a major problem for the concept of faster-than-light travel and time travel. This is one of the reasons why faster-than-light speed is considered impossible according to our current understanding of physics. The notion of time reversal and the potential for paradoxes it creates contradicts the principle of causality, the idea that cause precedes effect. In the world as we know it, effects don't happen before their causes. So if we were to travel faster than light and cause effects before their causes, we would be breaking not just the laws of physics, but also the fundamental order of the universe. In essence, going faster than light may not only break the laws of physics but also the fabric of time itself. The idea is as fascinating as it is perplexing, and while we continue to explore the mysteries of our universe, these paradoxes serve as a humbling reminder of the complexities and limitations of our current understanding. But are we sure nothing can go faster than light? This is a question that has puzzled scientists for decades, and it's a testament to the limitations of our current scientific understanding. We've come a long way in our understanding of the universe and its laws, but there are still phenomena that challenge our current theories and provoke us to think beyond our existing knowledge. One such phenomenon is quantum entanglement, a bizarre aspect of quantum physics where particles become interconnected. These entangled particles, no matter how far apart they are, can seemingly communicate with each other instantaneously, faster than the speed of light. This flies in the face of our current understanding of the universe, where nothing should be able to travel faster than light. Yet quantum entanglement has been experimentally confirmed over and over again. Then, there's the expansion of the universe. Observations suggest that distant galaxies are moving away from us at speeds exceeding the speed of light. This seems impossible according to Einstein's theory of relativity, but it's happening nonetheless. It's not that the galaxies themselves are moving faster than light, but rather the space between us and the galaxies is expanding, and it's expanding so rapidly that it exceeds the speed of light. These examples highlight how our current understanding of the universe is not complete. There are still mysteries that we have yet to unravel. We're like explorers in an unknown territory, armed with a map drawn from our observations and theories. But the map is not the territory. It's a representation, a model, a simplification of the actual territory. And as with any model, it has its limitations. So, while our current understanding suggests that going faster than light leads to time paradoxes, who knows what future discoveries may reveal. As we continue to push the boundaries of our knowledge, as we continue to explore the vast expanse of the universe, we may find that our understanding of the universe is not just limited, but also evolving.
Please do like, share, and subscribe to my channel. Thanks for watching.